Welcome to linear algebra, not just a world of symbols, but a playground of geometry, movement, and transformation. Grab a pen and paper. This isn't passive watching. You'll need them to solve the problems yourself. Think of vectors flying through space, matrices reshaping entire coordinate systems. Linear algebra is the language of geometry, and today we begin decoding it. So before we dive deeper, let's take a quick breath with some math humor. A new study revealed that 4 out of 3 people struggle with mathematics. Wait, what? That's right, 4 out of 3. If you're one of those 4, don't worry, we're here to fix that. And if you spotted the error instantly, congrats, you're always thinking like a mathematician. Let's start with the simplest building block, scalars. A scalar is a number that only has a size, or magnitude. It tells you how much, but not where. So scalars are just pure values, no arrows, no angles, no orientation, just numbers that scale things. For example, we have temperatures, like 30 degrees, it's hot, but it's not pointing anywhere. And like the weight, 50 kilograms, it's heavy, but it's also directionless. Now the speed, 60 kilometers, which is really fast, but without a heading. You're solving math problems like a champ, and then it hits you. You have 34 watermelons. Not 3, not 4, but 34. Suddenly you're a royalty, the watermelon emperor, sitting on a throne of fruit you never asked for. So back to business. In linear algebra, we move from scalars, just numbers, to vectors. So a vector is a list of numbers that represent something with magnitude and direction. Think of it like magnitude tells you how much and direction tells you which way. For example, we have a vector 4 and 2. So 4 we can imagine as x and 2 as y. So we go 4 units right and 2 units up. That's just the concept right here. Every vector can be broken down into components, horizontal and vertical. These are the x and y parts that make up the whole. If you know the vector's magnitude and direction, you can calculate its component. So Vx is equals to V into cos theta, and Vy is equals to V into sine theta. So the formula of cos theta is adjacent upon hypotenuse, and the formula of sine theta is opposite upon hypotenuse. And that's basically it from this. So let's break a vector into parts. Say we have a vector with magnitude 10 and angle theta is equal to 4 degrees. We want to find how much of it pointing horizontally, or x, and vertically, or y. Here's how. Vx is equal to 10 into cos theta is the formula, and for Vy, it is Vy is equal to 10 into sine theta, and that is the formula right here. And if we do the sum, approximately Vx should be equal to 7.07 and Vy should be equal to 6.42. And what if you already know the components and want to find the angle or the magnitude? So you can find the magnitude using V, which is equal to the square root, then Vx, or our x component, square plus y square, the y component. And now we know what our x and y are, so we put the square root, then 7.07 square plus 6.42 square, which is approximately equal to 9.54. And after all that trigonometry, let's check in with your emotional state. You're in a deep math problem solving for x and y, finding angles, calculating magnitudes, and then you see if math could grow up and solve its own problems. That would be great. And honestly, same. Math is the only subject where your problem become its problems, and you still don't get paid for solving them.
So let's start with a challenge. Draw a vector of magnitude 5 at an angle of 45 degrees. Your task is to find its x and y components. This is your first step into vector decomposition, where geometry meets algebra. So good luck solving, and make sure don't cheat for solutions because you'll practice, and if you can't solve, then I will give you the solutions. So just try for now. And you are allowed to pause the video so you can take as much time as possible. And yeah.
So here's how to solve it. So our magnitude is 5 and theta is 45 degrees. So Vx should be equal to 5 into cos theta, which is approximately equal to 3.53. And Vy should be equal to 5 into sine theta, and it should be approximately equal to 3.53 as well, since 45 degrees splits the vector evenly, so both the components are equal. So you've just built a symmetrical triangle, clean, elegant, and powerful. Now let's move on to vector operations. So vectors aren't just arrows, they're tools. We use operations to combine and manipulate them meaningfully. The three core actions are addition, subtraction, and scalar multiplication. So first of all, addition. Combine effects like motion or force. And subtraction. Find differences or displacements. And then scalar multiplication. Stretch or shrink a vector. So these operations are the grammar of the vector language, and you're learning to speak it. And now, you're deep in math vector, trigonometric functions, components, operations, and then you try to do it without a calculator. So trying to do a calculator is like really hard. You press your temples like a telepath, hoping sine or cosine will whisper the answers. Math, the only subject where brain becomes the hardware. Anyways, let's begin with the geometric view of addition. Vector addition uses tail-tip method or tip-to-tail method. So place the tail of B at the tip of B. No. Place the tail of B at the tip of A. The arrow from A's start to the B's end is the resultant. This shows the total effect of both vectors acting together, combining forces or steps. And remember, vector addition is commutative. A plus B is equals to B plus A. The order doesn't matter. Anyways, algebraic addition is simpler. So we add components by the component, x with x, y with y. Example, a is equals to 3, 4, 3 and minus 4, and b is equals to 1 and 2. So if we combine a plus b, 3 plus 1, and minus 4 plus 2, which should be equal to 4 and minus 2. So the components already encode the direction, so adding them directly gives the resultant vector. So vector subtraction now describes how to remove one vector from another. Algebraically, we subtract the component by component. Ax minus bx and ay minus by. So we have ax and ay, and from b we have bx and by. I mean, we just do the subtraction directly. So this gives the horizontal and vertical differences. The correction needed to go from B to A, it's the difference vector that shows displacement, error, or change. Now, geometrically, subtraction is the arrow from B's tip to A's tip. Let's solve it with an example. So plot A is equals to 2 and 4, and plot B is 3 and 4 on the grid. Draw a vector from the origin to 2 and 4, and then draw a vector B from the origin 3 and 5. Now connect the B's tip to A's tip, and that arrow is A minus B. Its coordinates are -1 and -1, exactly what we found algebraically. It points down and left. Left and down, whatever. So geometric correction from B to A is a thing. So yeah. Now you've drawn vectors, split them into components, and added them and subtracted them. And then it clicks. That moment in math class when everything suddenly makes sense, you just feel unstoppable. You feel like this: I'm the smartest man alive. Celebrate the moment because math clearly is the victory. Time for another challenge. Add the vectors 3 and 4 and -2 and 5. This is pure component-wise addition. X with X, Y with Y. Let's see what happens when we combine motion in different directions. So yeah, you can pause the video if you want and take as much time as possible because I'm just about to bring the solution. Here's how we solve it. A is equals to 3 and 4. B is equals to -2 and 5. So if you combine those, A plus B, then it should be equal to 3 plus -2 and 4 plus 5. And it should be equal to 1 and 9. So the result is a new vector pointing 1 unit right and 9 units up. That's the total effect of both vectors acting together. Now, about scalar multiplication. Now let's scale a vector. So scalar multiplication means multiplying a vector by a number. If Vx, meaning V is equals to X and Y, then KER, then KV or K multiplied by V should be Kx and Ky, meaning K multiplied with X and K multiplied by Y. This stretches or shrinks the vector. If K is greater than 0, then it remains the same direction. If K is less than 0, then direction flipped. And if K is equals to the 0, then collapse to the origin. For example, K is equals to 3, A is equals to 3 and 5, then Ka is equals to 9 and 5, 15, not 5. You've just scaled a vector by a factor of 3. Now, you're solving a math problem, the whole class is debating whether the answer is 17 or 18, and you got 157. That's when you realize you didn't just miss the mark, you launched into another dimension. Mistakes in mathematics are humbling, hilarious, and sometimes heroic. Anyways, back to business. Now let's try scalar multiplication yourself. So multiply the vector 2 and 3 by scalar -2. What happens when you flip the vector and stretch it? Now do it. You have again a lot of time if you want to pause it. and then I'm just gonna show you the solution if you don't know how to solve it. So here's the solution. K is equals to -2 and V is equals to 2 and 3. So KV should be equal to 2 into -2, 3 into -2. And the answer should be -4 and -6. The vector now points in the opposite direction, flipped and scaled. Now you've just turned a forward motion into a backward one. Now, let's recap what you have learned. So scalars, which are just magnitude, vectors, which are magnitude plus direction, components, break vectors into x and y, addition, combine effects, subtraction, find differences, scalar multiplication, stretch, shrink, and flip. Now, you're not just memorizing formulas, you're thinking geometrically, and that's the real power of linear algebra. And if you like this video, make sure to comment, and if you have any questions, then make sure to ask any of those, because I'm really active on YouTube right now, and since we are a small channel, I will make sure to reply any comment of yours. So, bye bye.